in about 30 seconds. Hello everybody and welcome to Science Live. We are coming to you today live from the Creation Museum in Petersburg, Kentucky. And it's a beautiful, lovely day outside for the moment, but we've got some storms forecast to come in, which for me is just another reminder of God's blessings, because yesterday we were out on the patio outside trying to shoot some rockets, have some fun with Dr. Faulkner, and the weather was beautiful and cooperative, and the sun was behind the clouds for better lighting, all of those things. So I woke up this morning praising God that the weather that we had yesterday was what it was and not what it is today with all the wind and everything. So we're glad that you're here with us today. I'm your host, Mr. Roger Patterson, and I'm joined today by Dr. Jennifer Rivera, and she's going to be accompanying me and keeping an eye on all of the comments and the feedback that you guys are providing. So if you would like to follow along on Ken Ham's Facebook page, we know that this is being broadcast on a bunch of different venues, but on Ken Ham's Facebook page, you'll be able to give your comments. And if you have a question about something we're discussing today, our topic is water and why it's so important that water can freeze. And you've got those questions, drop those in. Kids, if you want to add your name and your age, we'll try to give you a mention. We know you guys love to hear those things. We think of a lot of kids who've been joining us from different families. We got some people joining us now?
Yes, we do. Someone from Australia. We have
All
Dana
right.
from Australia, and we have someone from New York City.
All
Quarantine
right.
Central, they said. Craig from New York City
Yes.
is here as well.
Craig joins us about every day,
Yes.
I think. All right. So another thing that we want to begin the show with is we've kind of teased this a little bit. We started doing these live streams as the crisis kind of came and people were on a bit of a lockdown and sequestered in their homes, but we're going to be changing the format just a little bit. So rather than doing programs every day, beginning next week on May 5th, we're going to be broadcasting live on Tuesday and Thursday. And then on Fridays, we'll have a hands-on demonstration that you can do, something that you can build at home and understand these principles a little bit more. So the schedule is going to be adjusted from 5 times a week to twice a week. So be looking out for those details. And we know that those of you who are on the East Coast, it's 10 o'clock right now, you're up and bright-eyed and bushy-tailed. But think about those people in California. They'd have to wake up at 7 o'clock to be able to get this. So we're going to move the time into the afternoon slots, and we're going to be hosting this at 2 o'clock Eastern time. That'll give more opportunity for more families and more people to be engaged in the comments and interact with us live. And that's really what we want to do, is to be able to interact with you guys in these programs. So those are some changes that are coming up next week, and I'll keep reminding about those things through the week. And as we move into next Tuesday will be the beginning. And we have a new name for the program. The new name, we've been going with Science Live, which was a very generic, uncreative name. Unlocking Science is going to be the new name. And the idea is that we're trying to unlock all that God has created and understand more about his wonderful creation. So look out for those logos and new things coming next Tuesday. Unlocking Science will make its premiere. And we've also got an exciting new platform that we're going to be launching on Friday, and more information will be coming out about that. Some of you, our supporters, have probably already received those emails and maybe even tried it out. So lots of fun things coming for us. All right, so Dr. Vera, we've got people joining us now.
We have someone who says, Claude, don't you dare freeze him.
Oh, okay. So one of my little gimmicks, yesterday we launched Claude on a rocket. Today we've got Claude on ice.
I'm very concerned about him being on ice. We have Lily and Ava from Arkansas. They're here. Wendy, age 8. And then we also have people from Pittsburgh. Great. And Bethany, age 14, Jillian, 12, Ryan, and 10, all from Pennsylvania. So that's awesome.
I hope Luke's on there today. We would miss Luke. He's 11 now. He just turned 11 a few days ago.
People from Georgia.
Yeah.
So, yeah.
Okay, today we're going to be talking about the concept of water. And if you think about water, water is everywhere. We might say it's ubiquitous. There's a big dictionary word for you. And water is an amazing thing that God has given us, and it does all kinds of cool things. Now, we did an episode a few weeks ago where we talked about water, but there was a little glitch at the end and we didn't get it captured and saved. So you may have seen that live. We're going to repeat some of those basic principles today quickly. But the key idea we're going to talk about today has to do with why Claude is on ice. And so if we think about water, water is a molecule and it's made up of different atoms. So here are some models of a water molecule. So if we think about this molecule here, these two blue balls represent hydrogen atoms. Hydrogen's the smallest atom, the simplest substance in the universe. That's at the atomic level. There are smaller particles and things. And then this central red one represents then oxygen. So if you think about the formula for water, we often call water H2O. That stands for two hydrogens, H2, and one oxygen. That oxygen's here in the middle. So what are these green paddles sticking out here? Well, those represent a part of the atomic structure that we call the electron. So every atom, no matter what it is, whether it's hydrogen or oxygen or carbon or radon, any of those things, is made up of protons, neutrons, and electrons. And we'll have to talk about those things in more detail in other episodes. But this is one molecule of water. So a molecule is when multiple atoms are bonded together. So this little line right here represents a bond between the hydrogen and the oxygen atoms. Now, water is amazing because of the way that it's structured. And if we think about water molecules, we usually don't just have one water molecule laying around. Okay? If you even had a tablespoon of water, you would have trillions of water molecules inside of that tablespoon of water because those molecules are so small. But if we were to get these molecules together and put them into a group, what starts to happen is the molecules get attracted to one another. Now, the hydrogen and the oxygen both have electrons in them, but electrons can be shared between them in different ways. And oxygen is what we call an electron bully. It likes to steal electrons from other things. So if electrons are somebody's lunch, oxygen's the bully still in the lunch from the hydrogen. And it pulls the electrons toward it. So if it has more electrons toward it, and electrons are negative, that means one side of the molecule, let me grab my pointer here, the side of the molecule over here where the green paddles are is very negatively charged, and the side over here where the hydrogen atoms are is very positively charged. And that creates our big science word of the day, polarity. So polar molecules are molecules that have one side that's negative and one side that's positive. And what happens with positive and negative attracted objects? I think you know the answer to that. We have this little term in science, if I can grab this without knocking everything over here. There we go. Okay, opposites attract. So when we think about opposites attract, you might think of a magnet. So I've arranged these magnets here on this plastic tube, and if I go like this, you'll know that the magnets are pushing away from one another. So here, this magnet is actually repelling this one. So that tells me that this side of the magnet and this side of this magnet must have the same charges because like charges repel. So I want you to make a prediction. If I turn this top magnet over so that the opposites are close to one another, what's going to happen? They attract. And so inside of the magnets are different arrangements of electrons that cause them to attract to one another when they're oppositely charged. The same thing happens with these water molecules. So if we have a water molecule and this side of it's negative and this side of it's positive, this water molecule is going to be associated in this way so that this positively charged area is attracted to this negatively charged area. And they arrange themselves in different patterns based on the way those things, the particles are charged. Okay? Any questions coming in so far we might stop and answer?
Not questions. Lots of people saying they love the new title for the program. So that's, and one person's concerned that the water molecules are not social distancing.
Well, they're not. They get pretty close to one another.
Yes, they do.
Okay, another model I've got here to think about this. Substances like water, you guys are all pretty familiar with water, I'm sure, and things like isopropyl alcohol. These are both clear liquids. Okay, you can think of them as clear liquids, and at room temperature. And if we were to look in close, and we used these balls here to represent water molecules, and these balls over here to represent alcohol molecules, the alcohol molecules are not very polar. If I push them, you'll notice they kind of just float around. They don't stick to one another at all. They move apart. But if I come over here, the water molecules, you can see they all stay together in tight little groups. And it looks like they're sticking to one another. Now, the reason why these have magnets inside of them, so they're being attracted to one another, but this works as a model for the surface of water. So because water is polar, it has two different properties that we think of. Okay, a couple more big science words of the day: adhesion and cohesion. So these are terms that we covered in that previous video. But if you think of an adhesive, like tape or glue, that makes two different things stick to one another. So I might take a piece of paper, put glue on it, and then I could glue it to some glass or some wood or something like that. So that's adhesion between two different things. Cohesion is when the same things stick to one another. So if you think about a drop of water, I could grab this pipette here, and I could take and suck up a drop of water, and water will fall as a drop into the beaker, and it stays together as a little drop. So you think about raindrops falling from a cloud. Those water molecules inside the drop are sticking to one another. Okay? If we could put this on the edge of the glass, we'd see little drops of water running down the edge of the glass, and they stay connected to one another because the water molecules stick to one another. So that's called cohesion. And that makes water an amazing substance. Have you ever gone up to a little pond or a creek, and on the edge of it in the still water, you've seen little insects skittering across the pond, and you think, how in the world do they do that? I don't think I could do that. I've got pretty big feet, but I think I'd probably sink inside the water. So being able to walk on the water is because of the polar nature of water, because the molecules are polar and they form these hydrogen bonds between them. We get what we call surface tension. So if we come back to this model of the marbles here, all of these marbles are sticking together in a pretty tight fashion. Okay? If I were to add something heavy, my little rock right here, and I sit it on top of these marbles, it doesn't sink down in them, and I can tap it around, and it might kind of separate out some of them there. But if I do the same thing over here on this with the alcohol, it falls right through the middle. The difference is the molecules in the alcohol don't stick to one another, and the molecules in the water do. So the water molecules are much more cohesive, so they stick to one another a whole bunch. And that creates a property that we call surface tension. So heavier objects can float on the top of the water for a little bit, but if I push it down, it might be able to force through the water molecules a little bit. So let me try and demonstrate that for you with this little beaker of water here. And we're going to have to do a bit of shuffling. We're going to set these models carefully back over here without spilling the marbles all over the floor.
Don't want to lose your marbles today.
Don't lose your marbles. If I take this paper clip, which is more dense than the water, and I drop it in here, it's going to sink down to the bottom of the jar. Right? Because the metal in the paper clip is more dense than the water. But if I carefully place the same paper clip, the same size, on the surface of the water, oh, I didn't get it. That figures. I can make it float if my hands weren't shaky. Let's see if we can pull that up here. That's why I should have 3 of these ready to go, huh? Okay, we'll dry that off for a second, see if we can do this again. I'm going to try and carefully place it on the surface of here. And I made the paper clip float on the surface. And you might notice it looks like there's a little bubbly rim around there because the water molecules are sticking together so tightly that it's holding up the paper clip. If I were to break that surface tension at all, it would sink right down. Okay? So that's the principle called surface tension that water striders and things that float on the surface of water take advantage of. That's why raindrops can form in the sky. All right, questions coming in yet?
Good question. Someone wanted to know what happens to water droplets in space.
In space, okay. If there is no gravity, then there would be the water molecules themselves are still sticky, and they're going to stick to one another. So they would form little droplets. And rather than falling to the ground like a raindrop would, there's no gravity in empty space. Say we were inside of the International Space Station or somewhere, and they would just float around. You could probably find some interesting videos of astronauts in the space station or the space shuttle where they'll take a tube of water and they'll squirt it, and it'll go shooting across the room. Much like a squirt gun, but in slow motion. It's like slow motion squirt gun. And they just stay suspended in space, and they can kind of poke them and prod them and fun things you can do. But that's because the water molecules stick to one another, and there's no gravity to pull them down. So you get raindrops suspended in air. Kind of like what happens with fog, but that's very tiny micro droplets of water suspended. Okay. Another interesting thing this causes is what we call a meniscus. Okay, so if we come in here and you get down tight with the camera and we look right at this angle, you might notice that the water looks like it's curving up the sides of this little graduated cylinder. Now, as a scientist, if I'm trying to read measurements on that graduated cylinder and I want to look at those lines, where should I read it? Should I read it along the spot where it's at the bottom of the curve, at the top of the curve, in the middle? How should I read it? So we make these graduated cylinders in ways that the lines, these graduations that you can see here, are marked to match the curve of the water. Now, why does the water curve and stick to the sides of the glass like this? Well, the answer is in those two words we used a minute ago. There's cohesion between the water molecules and adhesion between the water molecules and the glass. So those two forces are causing the water molecules to stick together. So let me try to demonstrate that for you here with these marbles again. So imagine this little bookcase holder here. So this is a little thing you might put on a bookshelf to hold up books. It's made out of metal, so it's going to be attracted to these magnets. Imagine this is the side of the glass container, and these are water molecules, and I've got these water molecules down here, and they're sticking to themselves, but they're also sticking to the side of the container. So as I add those water molecules in there, you can notice that I can make a stack of water molecules up against the wall over here, and just like the water molecules were sticking to the glass in our graduated cylinder over there, these water molecules are sticking to the side. But I'll only be able to get so high, and then they'll start falling down because the forces of cohesion and adhesion have to be balancing one another out. So as I add these on here, we bring the camera angle down just a little bit, you might notice we're getting kind of a curve in the shape here. So this would be where the water molecules are sticking to the side of the glass in this area, and the water molecules are sticking to one another in here. So it makes this curve against the side of the glass. These are all things that are important for us to understand in science. Over here in this blue beaker, we can demonstrate this as well. Does that glass look pretty full to you? Would you want to have to carry that across the living room? Probably not, it might spill. But if I add more water to this, I can keep adding water, and because those water molecules will stick to one another, you might be able to see this is actually getting taller than the surface of the glass. And I'm going to put this piece of paper back here so that you can see that a little bit better. Okay, so this should allow you to see the curve there. You'll notice that the water is actually taller than the glass container it's in. How is that possible? Shouldn't gravity be pulling that down and making it spill over the edges? Well, the answer again is, we're getting close. The water molecules are sticking to one another. They're cohesive with those hydrogen bonds between them. At some point, I'll add enough water so that the force of gravity is stronger than the force of cohesion. Oh, we're getting really close. And one drop, there it goes, right over the edge. So now gravity, the force of gravity, has become stronger than that force of cohesion, and it pulls it down. So that balancing of forces.
Someone asked if there's anything you can add to water to make it more cohesive.
More cohesive. We can do things that would increase the surface tension. So, for example, could you blow bubbles with water? Kind of, okay, but they don't float in the air very well. If we add something like dish soap to it, or the bubble container solution, then we can increase the surface tension. So yeah, we could add substances that would either increase or decrease the stickiness and the surface tension of those different things.
And someone asked if its surface tension is the reason why we can float in water. That's from Gabrielle 11 and Sophia age 9.
Okay, we float in water based on density. Your body is much too heavy to be supported by the surface tension in a given area. Now, you might be able to get like a big sheet of plywood that was maybe 4 feet by 8 foot wide that weighed the same amount as you, because it has a lot more surface area. You might be able to get it to float on top of water, but because your surface area and your mass, that ratio has to be balanced so that it's less than the surface tension. So you don't float in water because you break the surface tension. You float in water because the density changes. So if you're in the water and you're kind of floating and you fill up your lungs with air, that makes your body less dense, and you'll probably feel your body rise up to the surface. You could even do this in the bathtub. If you go to a place like the Great Salt Lake or the Dead Sea, where there's a lot of salt in the water, then the density in the water is much higher and you're less, and so you actually float on top of the water. I grew up in the Salt Lake City area, so I've been in the Great Salt Lake, and to feel your body be buoyed up by that water is a very interesting feeling. Okay, so the key concept we want to get to today has to do with ice. So we're gonna look at ice a little bit here. God has made water in lots of amazing ways, and we're gonna do some more programs where we can talk more about the way that God's created water, because it's got so many amazing properties, and I just made a huge mess. We'll wipe that onto the floor and clean it up later. If we think about ice, ice is a unique substance. In almost every case, when we take a substance that's a liquid and we have a solid form of it, the solid form is more dense, so the molecules get closer together. So the density of the substance is determined on how close those molecules are packed together. Water has a density of 1 gram per cubic centimeter, right? But ice floats in water, so we know that it must have a density that's less than that. So if I think of, let's get this beaker back out here. Here's liquid water. We know that this water has a density of 1 gram per cubic centimeter. And if I take an ice cube here and I drop it in here, we can predict what's going to happen, but you probably already know the answer because you've done this before. It's going to float on the surface. Now it floats not because of the surface tension, but because of the density. So the density of the water allows this ice to float. Most substances, when they get in their solid form or they're cooled, they actually get more dense. Water is unique, and there are a few other things that will do this, but it actually gets less dense. That is an incredibly important concept for several reasons. If we think about putting like this container here, I stuck this in the freezer earlier. And if we take a look at it closely, we can see that the freezing is happening up here on the top, not down here in the bottom. There's nothing frozen down on the bottom. So imagine this were a lake or a pond, like the pond we have outside here at the Creation Museum. If this were not the case, and when this icy layer formed on top, it sank down to the bottom. I can't even push it down there, okay? If we could get it to sink down to the bottom, and then another layer froze on top and it sank down to the bottom, and another layer froze and sank down to the bottom, what would happen to all of the fish and all of the plants and all of the lobsters?
Yes.
Or little crayfish you might have living in a freshwater pond, which are actually just miniature lobsters.
Even the vegetation.
Yes, even the vegetation.
Yeah.
if this weren't the case, if God had designed the world in another way, he probably could have made it work because he's an amazing creator, but he designed it this way with very specific purposes. When the ice floats and it stays on top of the lake, that provides an environment down lower where the fish and plants and other animals can still live even during the period where it's frozen on top. Okay? If you've ever been ice fishing, you know this is true. We can bore a hole through the ice and go fishing and catch fish that are still active and living down in the lower part of the lake where it's not frozen on the surface. So this is an amazing design that God has given us in water. If this weren't the case, lakes would freeze from the bottom up and we wouldn't have fish. And then I wouldn't be able to go fly fishing after work to relax. That'd be a terrible thing.
Or have delicious lobster.
Yes, the lobsters would all be dead.
Yes.
Another thing that's unique about water when it freezes is if its density goes down, that means its volume must go up. So what would happen if I were to stick this bottle and I were to fill it up with water and I were to stick it inside the freezer? You may have done this before. Have you ever grabbed a can of soda and you wanted to get it cold real fast for dinner or maybe for an afternoon treat and you forget about it?
Yes.
And then at 11 o'clock, your mom comes screaming at you, "Why did you leave that soda in the freezer?" Because it made a big mess.
My kids have done that, yeah.
I've done that before too, I admit it. Okay. So what would happen to this if the water inside here, when it cools, expands, then we would get this situation. So if you notice these two bottles, these are the same bottles, but this one, you can see this giant bump formed over here where the water has expanded. Okay? And if we were to unscrew the cap, we could probably see that it's actually overflowed and filled up the top. Now when I filled this bottle, I filled it right down here to the bottom of this neck, but it's expanded so much, and it's melting a little now because we've had it out of the freezer, that it overfilled the container. Okay? So water expands when it freezes, and that allows its density to go down, and that's what allows it to float. This is very important in things like erosion. Okay? Water can actually get down in the cracks of rocks during the wintertime, and then it freezes. And when it freezes and expands inside the crack of a rock, it can crack the rock open. And this helps the natural cycle of breaking down rocks and building soil for us. So another way God's designed that to work.
Someone did ask if temperature can affect cohesion.
The temperature does change the cohesion. So if we were to plot a curve of the cohesion and even the density of water at different temperatures, I believe it's about 4 degrees Celsius, so just above the freezing point of 0, is when it's the most dense, the most cohesive. And then it forms these crystal structures as it turns to a solid, and then they're very cohesive. So they are bonded together, all right? This soda can over here represents what happens when you leave that soda inside the fridge. And you'll notice that this water expanded so much that it actually cracked the can. So it's strong enough to break that metal. That aluminum was actually torn by the force of water. So water is strong enough to tear metal, right? Over here, we can see that hasn't happened. You can also see that it's definitely domed up out here. So it froze and expanded. And this is why we don't leave soda cans in the freezer. And if it did get left in the freezer, it'd get that syrupy, sugary mess all over the place. And the carbonation could also cause it to spray everywhere and make a real mess. So these are things we want to be careful about in the future. Okay, any last questions before we wrap up for the day?
No, just lots of questions about poor Claude sitting in the ice.
He's okay.
He's
Claude
fine,
is just a plastic lobster. He'll be okay. But no, if he were a real lobster, we would treat him kindly, just like we do our animals in our zoo.
Yes.
So we'll have some fun with Claude. We'll launch him on rockets. We'll put him in ice, but it's just a fun gimmick. So as you're watching the show in the future, you can keep an eye out for Claude. He's usually hiding somewhere in the background doing something silly, and we'll try to bring him in. All right, well, we thank you guys for joining us today. We're glad we could teach you some of these things, and we've got more amazing things to teach you about how God has designed you, or has designed water in the world that He's created to function in lots of different ways, including in your body. A majority of your body is actually made up of water. Mm-hmm. So we'll talk about things like that and specific heat and differences in things in the future. But until then, we hope that you will keep watching these programs and enjoying them, and get out and explore God's creation and learn about all